Welcome to Nuclear Energy in Korea, a podcast to promote discussion of major issues and challenges in U.S. and Korean nuclear energy. I'm Alan Ahn, and I'll be your host today. I'm speaking today with Professor Joonhong Ahn with the Department of Nuclear Engineering at UC Berkeley. He has been with the faculty at Berkeley since 1995 and has led numerous joint research projects with organizations such as the IAEA and major institutions in Japan, South Korea, and the United States. Professor Ahn, thank you very much for joining us today.
Thank you very much for having me.
Professor Ahn, you're currently teaching at Berkeley, but I understand that you were born and raised in Japan and received your doctorate in nuclear engineering at both University of Tokyo and UC Berkeley.
Mm-hmm.
Could you speak a bit more about your background and academic career?
Sure. I was born in Osaka as a third-generation Korean. So my grandparents of both sides came from Gyeongsang-Namdo about 100 years ago to Japan. I was raised in Osaka until age of 18 and entered the University of Tokyo in 1977. And I graduated from Department of Nuclear Engineering with my bachelor's degree in 1981 and with my master's degree in 1983. And I entered the PhD program at UC Berkeley in 1983 while keeping my status as a graduate student at the University of Tokyo. And I obtained my PhD degree in May 1988 and returned to the University of Tokyo after that. And I completed a doctoral program in Tokyo and obtained a Doctor of Engineering degree in March 1989. Around that time, I got the fund for my postdoctoral research from Japan Society for Promotion of Sciences, or JSPS. It's a kind of counterpart of National Science Foundation in the United States between the time period of 1988 and 1990. And after that, I became a faculty member of the University of Tokyo as the first non-Japanese without limited duration of employment. In 1993, I moved to Tokai University as an assistant professor. And finally, in 1995, I joined the faculty of UC Berkeley. And since then, I have been serving as the regular faculty member of the department. At UC Berkeley, my academic supervisor was Professor Thomas H. Pickford, a famous scholar in the field of nuclear fuel cycle and radioactive waste management. At the University of Tokyo, the Professor Atsuyuki Suzuki was my advisor, who was the former chairman of the Japanese Nuclear Safety Commission and currently the president of the Japan Atomic Energy Agency. So that's my background.
Your research interests at Berkeley revolve around analyses and performance assessments of geological disposal and nuclear fuel cycle options. Mm-hmm. So for a country with a civil nuclear program, what are the main considerations in determining what path to take with regards to the various fuel cycle and disposal alternatives?
First of all, it is very important to clearly understand the motivations for development of civil nuclear program. Why do we want to have nuclear power? And this is because regardless of whether the prospective nuclear program is small or big, the commitment will last more than a century, very likely multiple centuries. So this is a serious, substantial commitment for a country. Of course, in such a long term, internal or domestic and external or international conditions change. So it is very important to have flexibility in the development. There is no such state as a steady state in any nuclear program. It is very dynamic. For example, as we observed in Japan last 2 years, things can change very quickly and sometimes very catastrophically. Thus, we need to implement high level of robustness and the resilience in the system. We also need to have capability of monitoring subtle changes in internal and external conditions and situations, and the capability of reframing a way of thinking and reforming the system. Naturally and obviously, the Japanese systems lacked that kind of feature. More concretely, most countries would consider introduction of nuclear power for their independence and the security or stable energy supply. We need to make the nuclear power system consisting of reactors, fuel cycles, and final disposal systems to achieve such goals with a high resilience and robustness. So that's a very conceptual response to your question. Maybe we would have some opportunity to come back to more individual, concrete matters.
Let's go on to a specific case then. For the United States, spent fuel management policy has been in flux as a result of the cancellation of Yucca Mountain. Mm-hmm. The release of the Blue Ribbon Commission report sheds some light on possible future directions in the U.S. But from your expertise, what would be your recommendations for current U.S. spent fuel policy?
Well, U.S. has been developing technologies and concepts of geological disposal for many years, since 1950s. Many important and crucial findings and developments were made in its history. So it was very much a pity that Yucca Mountain project could not complete as it was planned. I do not think that this happened because of the lack of scientific basis. Rather, I think this happened because some of the external and the internal conditions surrounding Yucca Mountain and the geological disposal itself had changed since those programs and policies were set. Of course, those plans were reviewed and modified in the past many times, and that is actually an indication of flexibility implemented in the programs and policies. Speaking of flexibility, the concept of geological disposal itself has evolved a lot since 1950s. It started as a very simplistic barrier of radioactive materials and salt mine, and now we have a much more sophisticated and complicated and a very flexible system which can be built in almost any kind of geological medium. So I think that we are very much close to actual realization of geological repositories in the United States, but there are still some features that need to be adjusted and fit into societal conditions and needs. I believe that the current concept of geological disposal has enough flexibility to accommodate such social boundary conditions. It's like we have developed a prototype of an artifact, and now we need to listen to customers to meet their needs, demands, and the preferences.
Going back specifically to Yucca, what are the pros and cons of Yucca relative to that of other possible options for the U.S., let's say, using a site like WIPP to store spent fuel or dispose of spent fuel?
Well, first of all, the Yucca Mountain is a very unique site if you look around the world, in the sense that Yucca Mountain repository is planned in an oxidizing environment. And with that oxidizing environment, the material alteration and degradation is different from those in a reducing environment, which is a condition for any other geological repository concepts. And so, and the oxidizing environment gives an interesting feature to the geological and Yucca Mountain geological repository. It often thought that because oxidizing environment gives a faster degradation of the materials in the repository Yucca Mountain repository is not so good as other repositories, particularly in a granitic repository or salt repository. But if you take a look at the sensitivity of the performance to the efforts that we could make in the fuel cycle part, the sensitivity is highest is high with the Yucca Mountain repository than other repositories. So if you do an effort to reduce the mass of the highly toxic actinides in the waste, you can actually reduce or improve the performance of the repository almost proportionally. So in a sense, the Yucca Mountain is very suitable or ideal to couple with fuel cycle options. On the other hand, the granitic repository or other very stable geological conditions give almost no sensitivity to the efforts that we could make in the fuel cycle side. So Yucca Mountain is a very unique and interesting option, but again, it's up to the public interest and demand. What kind of repository or what kind of safety level we would like to achieve, and another question would be, how much do we want to spend now to get a certain level of safety in the future and now? So it's a more complicated question than we thought in the past, and in that regard, we really need to listen to the public.
What information do you believe needs to be conveyed to the public in order to perform an accurate risk-benefit assessment that takes into account, these societal needs that you've mentioned?
I think the efforts for the performance assessment that we did so far provide very useful materials and information for public discussions and judgment, but probably it was still kind of limited and one-sided. That I mean that the performance measure in the performance assessment has been the radiological risk or exposure dose rate, annual dose to the public. But the geological repository has many other features and characteristics, and so we need to develop a suite of performance measures to understand the performance of the repository more comprehensively. And that might include a cost, that might include the necessity of some kind of pretreatment. Altogether, the public can make a more informed judgment. So we need to develop a more comprehensive and multifaceted performance assessment technologies to provide more integrated information with the public.
Speaking about repositories in general, there have only been 3 successful cases of final disposal for spent fuel, high-level waste, transuranic waste, namely WIP, Onkalo, and Forsmark. What lessons can we derive from these cases to ensure that we have more such successful sites in the future?
I can see the excellent geological stability in any of these 3 cases. That made the performance assessment very simple and straightforward. That made the public understand very easily how the repository would behave and what kind of safety the repository can achieve. So it is always beneficial for any repository program to have a good, stable geological formations. And then I noticed that all of these 3 programs have had an excellent program to communicate with the public. And there was a good leadership to coordinate such a communication among the stakeholders. So I think this is kind of engineering program to match the need among the public and adjust the technologies to meet the public needs and find a solution and a plan for achieving that. So this is very much like what an entrepreneurs do in their startup business.
Speaking of communication with the public and engaging all the relevant stakeholders, and going back to the case of Japan, and obviously you have your expertise in the Japanese case, you have your roots, your academic background there, and you've traveled extensively to Japan recently.
Mm.
What is your opinion on how the Japanese government can balance its obligations to Aomori Prefecture and duties to manage spent fuel, especially given the uncertainties about Japan's nuclear future?
Well, that's a very tough question. Again, I think they meaning Japanese people and Japanese government needs to reconsider and redefine why they want to have a nuclear power, or they want to keep the nuclear power option. Once they could have a good discussion about it, they need to consider how that Rokasho facility can fit into their future program. But regardless of future scenarios, it would be necessary for them to have responsible plans for at least existing nuclear fuels and wastes. So even if they decide to phase out nuclear power, there is still a good reason or meaning for them to keep the Rokasho facility. And this is, again, an issue of balance between the risk and benefits of this generation and future generation. If they, meaning Japanese people, don't want to spend any more money to nuclear power and sending all the risks to the future generations, that's one way, that's one option. But if they want to make the future risk significantly reduced and make the future better and more safe, I'm sure they need to keep technical options like Aomori Rokasho facility. So to me, it seems that they need a very detailed, fundamental discussions of the motivation for their nuclear power first.
Kind of going along with this theme of Rokasho and making things better for future generations, you said that we need final disposal that realizes higher robustness, obviously the term that you've used throughout our discussion today, higher safety, and minimize our reliance on natural barriers. What technologies and innovations, in addition to the ones that you've mentioned, lead us towards this direction?
For the reduction of the future risk and potential hazard to the people can be made in basically two ways. One is to make the waste form or waste canisters more robust so that the radioactive materials won't go into the natural environment or geological formations or groundwater system. The second way is to reduce the source itself. When we say, when we observe the spent fuel from light water reactors, the most of the hazard or toxicity comes from the minor actinides. And so for that, we can consider coupling of some reactors, for example, to transmute those highly toxic actinides. And so the resultant waste could have much less toxicity from the first place. So then the more practical question is how much or how we can combine these two options when we consider an actual repository system or waste management system at large. So when we consider the waste geological disposal, we need to include the treatment stage or the fuel cycle stage altogether, including the cost and the benefit and the risk of those operations.
Turning to the Korean case, South Korea is currently seeking development of pyroprocessing, justifying it mainly on the basis of, being able to reduce the repository volume necessary for final geological disposal. How does pyroprocessing fit in, maybe perhaps provide other benefits, let's say, with regards to improving the robustness and safety of disposal in Korea?
Well, first of all, pyroprocessing gives an opportunity to manage each group of radionuclides separately, and we can tailor suitable robust waste materials. And also, for some group of radionuclides, like minor actinides, we can consider transmutation. So pyroprocessing is kind of a prerequisite for more comprehensive treatment and management of the waste. Without that, we just have one option of direct disposal of spent fuel of light water reactors. And this lack of variety would be really bad for decision making and policy making. So in that regard, I think pyroprocessing is a very important step for Korea to consider their future nuclear program. More concretely, by separating actinides, they can consider transmutation in a fast reactor, for example, so that actinides can be transmuted. The remaining fission products from light water reactor spent fuel can be solidified into more robust materials like ceramic waste form. And because we could reduce the volume of the fuel, spent fuel or radioactive waste with a significant factor, we could consider some special options like deep borehole disposal for some particular radionuclides of concern, such as iodine and selenium and other things, which are mobile in geological formation. But without pyroprocessing or any kind of separation technologies, all these options are not available. So the pyroprocessing would be a very important gateway for much greater variety for future decisions.
Well, looking towards the future,
yeah.
Korea's ultimate vision is to eventually develop a pyro fast reactor fuel cycle.
Mm-hmm.
However, you have many in the U.S. that argue that Korea has yet to sufficiently progress in its fast reactor development. Can pyroprocessing play an immediate role in addressing Korea's spent fuel challenges while fast reactor technologies remain in development? Specifically, many of Korea's spent fuel pools right now are reaching a certain saturation or capacity.
Well, if you make a separation in any way, including pyroprocessing, you have many options from there. It doesn't have to be limited to the fast reactors.
Okay.
You can have a recycle to light water reactors, for example. You can consider burning plutonium and other actinides in different types of reactors, such as high temperature reactor with trisul fuels. So we can consider many different options. And actually, that kind of variety in reactor stages would also be very important. If you have just a single reactor type, and if something went wrong with that reactor type, you have to shut down the reactors, the fleet of reactors altogether for many days. And that's a very risky situation. So if you have a variety of reactors, you can increase the robustness or resilience or flexibility of the whole fleet of nuclear power plants. So the pyroprocessing doesn't have to be coupled with the fast reactors, but can actually be combined with many other different types of reactors. But it is very reasonable to have fast reactors, especially when we consider the sustainability of nuclear power future or sustainability of nuclear fuel resource in the future. So again, it depends on what kind of need and conditions a country existing or living with. So again, the pyroprocessing can open up all these variety and flexibility.
You mentioned earlier that the concept of geological disposal is evolving from when it was early on, let's say in the 50s, and One of the emerging issues in geological disposal is severe scenarios, unknown unknowns, and how they may create situations leading to radioactivity release into the environment. What specifically are we talking about with regards to severe scenarios? Are we talking about seismic activity, presence of groundwater? I know earlier you mentioned oxidizing versus reducing environments.
Okay, all these are known unknowns. Okay, so as far as you can say what they are known unknowns. We just don't know how severe that could be. Okay. The more serious issue is the unknown unknowns. Okay, the unknown unknowns I think is referring to that we don't know how that could happen. Mm-hmm. Okay, but if you look at the consequence side, we pretty much know what can happen. We can envision the kind of worst case scenario for a given geological repository design. We know how much nuclear fuels and high-level waste would be put into a geological repository. So if you assume that all these radioactive materials are out, how much damage or risk would people get? That's relatively reasonable. I mean, I shouldn't say easy, but possible to envision. But we do not know how that can happen. Like we didn't know how the Fukushima accident could happen like that before the accident happened. So we do not know how it could happen, but we probably know much better what would be the consequences of severe accidents. And now we, like Fukushima, we now know that which radionuclides would be mobile in the natural environment, such as iodine, cesium, and some other few nuclides. So the question would be, how can we confine those radionuclides? And if they are released, how can we minimize the impacts of those radionuclides to the human health and societal activities? So I think again, we can cope with these things by reducing the source term and by increasing the robustness of the waste form, or increasing the level of sequestration of those radionuclides in geological repository. So all this done, we still have some residual risk, and there we need a very careful and deep discussion with the public stakeholders. To what extent we need to do to sequestrate the radionuclides, but if something gets out, how can we mitigate those things? And basically, the reason why we take such a long time to achieve actual repository construction is because we took so much time to find an agreement point with the public about this issue. And as an engineer, what we can do is to work for those engineering options that reduces the source and increases the robustness of the waste form.
Professor Ahn, this has been a tremendously fascinating and insightful talk. Thank you so much for sharing your expertise and knowledge, and as well as your time.
Thank you very much. It was my pleasure.